Hello, everyone, and thank you for joining us for today's FreeFlyer 7.10 release webinar. And before we begin, we have a few housekeeping notes. All attendees are muted. Cameras will remain off throughout the session. The webinar is being recorded and will be posted on our YouTube channel. We'll also share the slides with all registrants after the session. And if you have any questions during the presentation, please feel free to use the chat function. We'll hold a Q&A session at the end to address as many of your questions as time allows. We're excited to have three speakers with us today. First up is Dr. Nathan Griffith, Senior Space Product Software Engineer at AI Solutions. Dr. Griffith earned his PhD in cosmic ray physics from the Ohio State University in 2015. He joined Leo Labs in 2016 as their primary orbit determination engineer and came to AI Solutions in 2024. Since then, he has led the development of FreeFlyer's new optical communication modeling capability. Next, we'll hear from Luke Schoenwetter, Space Product Software Engineer. Luke holds both bachelor's and a master's degree in aerospace engineering from the University of Alabama, where he conducted research in the Astrodynamic Space Research Laboratory. His work focused on orbital mechanics, trajectory optimization, and differential games. At AI Solutions, Luke is part of the FreeFlyer development team and specializes in numerical solution methods for trajectory design. And finally, we have Nate McCown, Product Support Manager. Nate leads the technical support team and training for FreeFlyer, helping users solve complex astrodynamic challenges. He studied at the University of Alabama, where he also conducted research in constellation optimization and remote sensing. Professionally, Nate has supported missions like the James Webb Space Telescope and is a key link between FreeFlyer's engineering team and our customer base, contributing both user engagement and product directions. And as for our agenda today, we'll have Nathan go over optical communications. Luke will showcase our multi-objective optimization capability. And lastly, Nate will highlight new features coming in FreeFlyer 7.10 and walk through our new sample mission plans. With that, I'll hand it off to our first presenter, Dr. Nathan Griffith.
Yeah, thanks, Regis, for the intro. So I wanted to start off talking about optical communications by kind of motivating why you might select optical communications components rather than the traditional RF-based ones for your communication system on a spacecraft. So with optical comms, kind of the main thing, right, is we're using much smaller wavelengths, and those wavelengths are kind of set the characteristic sizes of the components involved. So that means as you move from RF communications down to much smaller optical wavelengths, you get much smaller size of your components, which means you get reduced weight. And because with optical components, you have a very narrow, bright beam, that means you can also get by with less power. So right away, your swap considerations go down. The good news is you can also achieve high data rates using these reduced size, weight, and power components. Another interesting feature of optical comms is that it's intrinsically more secure from a physical perspective. For instance, high gain antenna for an RF system might create a beam on the ground that covers a few states. But with an optical system, you could maybe tune that down to a few hundred meters. So there's just less ability for people on the ground to intercept your signal. All right, so what kind of questions might we want to ask as we're considering optical comms for our use case? Well, the obvious one is how much data can we transmit? Obviously, that's the name of the game. That's what we want to do. And then additionally, depending on our mission parameters, we might be interested in how far we could possibly transmit that data. And then finally, the question is, what could prevent us? What are our kind of complications from transmitting data as fast as we want and as far as we want? So you can see on the right here that, spoiler, we do have to consider the atmosphere quite a bit as we concern ourselves with optical comms. All right, so as we're talking about the challenges of optical communications, one of the things that's useful to consider is this mathematical construct called the link margin. And the link margin runs all the way from the power of the transmitter over to the sensitivity of the receiver on the right. And then in the middle, you get all these terms that come from either gains or losses that you accrue along the way. So if you calculate your link margin and it comes out positive, that means you're beating the point that you need to hit in order to achieve your performance threshold. But if you run this equation and it comes up negative, that means that you have some work to do in order to make up some of the losses that you're accruing along the way and tweak some of these parameters in this chain. All right, so we'll walk through some of the stuff in that equation. I just showed the link margin one, and we'll start with the positive terms. The gains come from your transmitter and your receiver. So the transmitters are lasers, obviously. Everyone's held a laser pointer before, and they know how narrow and bright that beam is. And that's kind of the main thing that makes optical communications so attractive. So basically, your beam width is going to set your gain on your transmitter. And on the receive side, that's also a pretty, commonly encountered object. The bulk of a receiver and the thing that sets the gain of it primarily is going to be just an optical component that's like, identical to a telescope. So on the receive side, it's going to be the diameter of your telescope that sets the gain. All right, so moving on to losses, one we definitely have to consider and that you'll encounter no matter what your context is, if you're in RF or optical communications, you have to consider free space loss, and free space loss is just a geometric inevitability of propagating radiation across subsequently larger surface areas of a sphere. So we have to take that into account, and we do. That's kind of the easy one we just knock out of the way. Okay, so we'll step through a few different features of the atmosphere, which I said we had to concern ourselves with. So if you know a little bit about atmospheric physics, but you're new to optical communications, kind of one of the off the top of your head questions might be, doesn't the atmosphere absorb certain wavelengths of light? How do we make sure that doesn't destroy our signal? So you'd be totally right. And due to the distribution of various molecules of gas in the Earth's atmosphere, there are certain wavelengths of light that are strongly attenuated. So the good news is there are also, you can see on the right here in this plot, various windows, and they're literally called optical windows, through which light passes pretty much unattenuated. So the good news is, yes, you have to keep it in mind, but as long as you do your engineering carefully, or you'll likely be selecting some kind of pre-made components along the way as you set up your optical system, those will tend to fall within one of these optical windows. So I've called it here 1550 nanometers. That's an extremely popular wavelength to select for free space optical communications, both terrestrial and in space. So again, if you're using prefab components, chances are very good you'll get something like 1550 nanometers, and this won't be an issue for you. All right, so one that we can't disregard just via engineering and part component selection is atmospheric loss due to scattering. The good news is that this is pretty easily parameterized in terms of a variable called the meteorological visibility, and that is just what it sounds like. It's how far you can see, although it's rigorously defined, but it's how far you can see. This is a very commonly available metric. For instance, basically all airports will report this because it's very relevant to the safety of air travel. And yes, you take in, you can compute the relevant parts that you'll need to calculate this attenuation based on the visibility and the wavelength, and then the relevant distance through a troposphere. And then finally, the third thing we'll consider about atmospheric propagation is an even more subtle effect called the atmospheric scintillation. And atmospheric scintillation is an effect that occurs where if your beam is propagating through the Earth's atmosphere, it's going to hit little bubbles of warm air. And as it passes through those bubbles, the signal that's going through is going to distort both in space and in time. It's going to introduce some variation. So you can see here on the right, these are a couple amateur astronomer photos I took. The one on the left is a night with very little turbulence, little scintillation, and the one on the right has more scintillation. So you can see it makes the difference between a very clear picture and a pretty blurry one. So, like I said, not only does it cause those spatial variations, it also causes time series variations in the intensity of your power. So in FreeFlyer, we give you a couple different ways to handle scintillation, and I'll spare you the really nasty line interval it takes to do this. But basically what you can do is come in with your system and say, I want to be sure that scintillation doesn't bother me, that it doesn't fluctuate in a way that hurts me 99.99% of the time. So you put in your system parameters, that percentage uptime you want, and then you'll get out an additional link margin you need to add in order to make sure that you hit that performance criterion that you put in. And you can also go the other way where you show up with your system and you calculate your link margin and you say, this is the link margin I have. Now tell me how often scintillation is going to bite me in this scenario. So those are the two different ways we handle it. Okay, so moving on to the receiver side, we'll talk a little bit about modulation. There are a number of modulations you can use for free space optical communications. Luckily, from a conceptual point of view, they don't get too sophisticated. We tend to not make it too complicated for optical comms versus RF communications. So here we're stepping through a few different popular choices for amplitude-based modulations. One of those is the simplest you could think of off the top of your head, and that's on-off keying, and that's laser on, it's a 1, laser off, it's a 0, and then you can set the timing of how long the laser on lasts, and that gives you a couple of different variations that are kind of cartooned out here. Another one is something called pulse position modulation, which basically means you time the laser and you blink it in a way that it corresponds to the data you want to send. This ends up being a very popular one for spacecraft because you end up blinking the laser less, which means you consume less power. So if power is one of your considerations, pulse position modulation is a pretty popular format. And then on the next slide, we'll talk through just a really simple phase modulation that we also include in FreeFlyer. Again, we don't typically, the modulations are not very sophisticated for laser communications. So this one is something called differential shift keying, differential phase shift keying. And basically that means you have one phase that corresponds to a certain symbol, and then you shift the phase by 180 degrees versus the last one. And that means that you're now sending the other symbol. So you switch from, for instance, 0 to 1. And in that fashion, you can kind of wobble the phase back and forth and send the binary data that you want to. Okay, so again, going one step deeper into receivers, there's roughly kind of two large families of receiver that we handle in FreeFlyer. One is direct detection, and those are relevant to the amplitude modulations that I showed a couple slides back. And a really popular one, which is kind of a cartoon on the right here, very simple cartoon, is you use a component called a photodiode. Here it's an avalanche photodiode, which is a very popular component. And that avalanche photodiode takes the incoming photons and it transmits them into an electrical signal based on the intensity. And then from there you can do your signal processing. So that's kind of the direct detection world. We also model some coherent detectors, which if you come from an RF background, you're probably familiar with hearing about heterodyne and homodyne receivers, and that's this kind of receiver where the incoming light is mixed in with a local oscillator, and then you process it from there. And then finally on receivers, we'll go one step deeper, and I won't spend too much time on this because people don't love staring at math. But this is just to kind of show you the way that the internal model for avalanche photodiodes, which were that popular component that I mentioned on the last slide, how those are modeled and how we might calculate the SNR sensitivity for that. So on the top here, you see that the incoming signal power, and then for APDs, they're a little bit special. They have to consider two different sources of noise. So you have to consider both shot noise and thermal noise. So those are included on the bottom. And yeah, that's just one example of the models that we include for different receiver types in FreeFlyer 7.10. Okay, so we've talked through a lot of different considerations for designing and implementing an optical communications-based system. And we've talked about how FreeFlyer 7.10 handles those. And having worked on this the last year, I'm super excited to see what people do with these capabilities as the new FreeFlyer comes out. And yeah, I can't wait for it. All right, so now I will hand it off to Luke, and we'll be talking through the multi-objective optimization features that are coming to FreeFlyer 7.10.
Yep, thanks, Nathan. Hello, everybody. My name is Luke. I work on the FreeFlyer development team, and today I'll be talking through the new multi-objective optimization features that are coming in FreeFlyer 7.10. Back in FreeFlyer 7.6, we added a generic optimization interface. It allows you to do very basic optimization. We added trajectory optimization, specific things in FreeFlyer 7.8. We added an optimal control suite. And then again, now in FreeFlyer 7.10, now we're adding multi-objective optimization. So in order to wrap our heads around what multi-objective optimization is, I'm going to pose an example problem for us to think through. So let's say that we have a spacecraft and it's on Earth, and we want to launch and visit 3 particular asteroids from a cloud of a number of different asteroids that are potential destinations. And we want to stay at each of those asteroids for a certain amount of time, and we have we want a 3 burn transfer in between each of those asteroids. And now, depending on which asteroids we choose from the cloud, those are going to determine what the total transit time and total delta V of the trip is going to be. So, say we go from asteroid 14 to asteroid 2 to asteroid 22. That's going to give us a certain total transit time and certain delta V. And if we pick a different sequence of 3 asteroids, that is going to change what that total transit time and delta V ends up being. So in terms of, if we plot all of the solutions for, in terms of transit time and delta V, we're going to end up with solutions that are non-dominated. And what non-dominated means is that there are no solutions that beat out this solution in terms of both objectives. So what we call that is the Pareto front. So in the figure here, you can see that the Pareto front represents the line past which there are no solutions to the left and lower corner of the plot. In other words, there are no solutions that are better in both objectives than any of those solutions in the Pareto front. So they're non-dominated. And so yeah, delta V and transit time. We want to figure out what the Pareto front looks like. We want to be able to, have that in front of us as an engineer so we can make an informed decision about what solution along the Pareto front works best for whatever our mission is. So how do we find the Pareto front? We're going to start with variables, and the variables in this problem are going to be the asteroid choice variables. In other words, which asteroids are we going to visit? We're going to need to make a choice for each of the tour destinations. Then we'll need to define some function f that is going to take those variables as an input, and it's going to output the delta V and the transit time for the entire tour. And that function is going to look something like this, where we are solving like a shooting problem that, again, is going to include 3 burns for this particular example problem. So there'll be a departure burn, a mid-course burn, and an arrival burn. And we'll minimize delta V in this sub-problem. But then that, that function is going to output the total delta V as we sum it, going from Earth to asteroid 1, and then from asteroid 2 to asteroid, from asteroid 1 to 2, and so on from 2 to 3. And then, solving all 3 of those sub-problems, we'll then have delta V's for each segment and transit times for each segment, and then we can sum them, and that ends up being the objectives that are being considered in the Pareto front evaluation. So the back side of the multi-objective optimizer is something called a genetic algorithm. And the way that the genetic algorithm works is first randomly generate a list of candidate solutions. And we call that the initial population. So each row in this matrix that we're looking at represents a sequence of 3 asteroids that we could visit. And then that function is going to evaluate all of those population members, and it's going to spit out delta V, and it's going to spit out transit time for each of those tours. And we can notice right away that there's actually Pareto domination occurring in this initial population. And by that I mean that solution 2 here has both a better delta V and a better transit time than solution 4. In other words, it is solution 2 dominates solution 4. Which, going back to our figure that we were looking at, solution 2 might lie on the Pareto front, whereas solution 4 certainly does not lie on the Pareto front because we've already determined it to be dominated by another solution. So we've evaluated this initial population, and what we now want to do is we want to come up with a new population that hopefully is better than the current one. So what we'll do in pursuit of that is we are going to look for solutions that we consider to be favorable. Solution one has next slide, Reese. Solution one has a great transit time. So the last solution in the list has a great delta V. So we will isolate those solutions, and we're going to do what's called recombination. In other words, we're going to take different pieces of each solution, and we're going to squash them together, and hopefully, next slide, Reese. Hopefully what we end up with is a solution that retains all of the favorable characteristics from the two parent solutions, and it doesn't retain any of the unfavorable characteristics of the parent solutions. Now, that is going to be, sometimes the case, and most of the time it's not going to be the case. But because of the power of the modern CPU, we can do that operation over and over again very rapidly. And over time, we'll find instances where that does occur, where we retain favorable traits from both solutions and we end up with a better recombined solution. So, Regis, can you go back to the previous slide, please? So we have that initial population. We're going to use genetic operations to come up with a new population, and from there the cycle just repeats until we intervene and stop it based on what the solution set looks like. Oh, yeah, okay. So to recap, we start by computing all of the objectives for the population. Next slide, Regis. And then we're going to evaluate how the Pareto front has expanded, how we found any solutions that beat out the previous Pareto front. Next slide, Regis. And then we are going to use those genetic operators to come up with a new offspring population from that parent population. And again, from there, the cycle continues from there, and it continues until we decide to stop it based on how much progress the multi-objective optimizer has made and whether the solutions that it finds are fitting for whatever our use case is. And to kind of close things out on multi-objective optimization, this is a new way to do trade study analyses in FreeFlyer. So, if I have a problem in front of me where I need to decide what my input variables are going to be for my mission, for my model, whatever it is, and I want to do that based on several different objectives, several different categories that I want to optimize for. The multi-objective optimizer allows you to easily and visually represent what that trade-off looks like so that you as the engineer can make an informed decision on what those input variables should be. And additionally, it adds a new way for handling discrete state spaces. In other words, problems where you have discrete choices like this asteroid tour problem. Choosing asteroid 1 versus asteroid 2, there's no in between, right? There's no asteroid 1.5. So that represents a discrete choice. And the way that the multi-objective optimizer works, it offers you a great way for handling those types of discrete problems. So that's all for multi-objective optimization in FreeFlyer 7.10. And we can't wait to see how you guys use those features.
All right, thank you, Luke, for walking through multi-objective optimization, and thank you, Nathan, for going through optical communications, both of which are going to be major headlining features in the upcoming release of FreeFlyer 7.10, but that's not all that we're including. Underneath the optimization branch here, you can see not only the multi-objective optimization features, but we've also included integrated trajectory phases. This new feature will allow users to now choose between integration-based dynamical enforcement using the dynamical enforcement method property. In addition to that, we've also added a minimum norm solver, and adding the support for the minimum norm solver essentially is a lightweight alternative to FreeFlyer's previously supported optimization engines. It's focused solely on solving constraints without considering the objective value and includes configurable options such as line search and bound enforcement methods, allowing users to control step handling and feasibility enhancement during constraint solving. Outside of that, we've also added DSN pseudonoise ranging support, and not as flashy, but also very important, we've included Red Hat 9 official support. Looking into some of the new sample mission plans in FreeFlyer, we've included 15 with the FreeFlyer 7.10 release, most of which are going to be focused on the new features that Nathan and Luke just walked through. 6 for the new optical link object, which focus on various combinations of links. So things like ground station on the moon, spacecraft to ground station focusing on the atmospheric losses that Nathan alluded to, interplanetary analysis covering both spacecraft orbiting Mars and Venus, as well as intersatellite links for constellations around Earth. Under the multi-objective optimization side, you'll see that we have 4 new sample mission plans included. We'll cover the asteroid tour in more detail, but we've also included examples for scheduling contacts between a constellation and a set of ground stations, as well as classical optimization problems like the traveling salesman and Schaeffer's second problem, which is a single variable problem with 2 objectives to be minimized. We'll talk more about the multiple impulse rendezvous sample mission plan in a bit, but outside of the mission plans focused on new features, we've also included sample mission plans for modeling constellations around celestial bodies other than Earth, modeling a distant retrograde orbit or DRO in FreeFlyer, reading in a CCSDS OPM, and a new procedure to display a 2-dimensional dataset with a heat map. Looking into our first sample mission plan here, we have the Optical Link Walker Constellation sample mission plan. This mission plan demonstrates the use of the new optical link object to analyze intersatellite links of a Walker constellation. It presents a Walker constellation where the user gets to select a transmitter spacecraft with a narrow laser beam, and the rest of the spacecraft are representative of receivers. The optical link is set up using an OOK-RZ modulation type and a near-infrared wavelength of 1550 nanometers. The view window on the left-hand side here showcases the intersatellite links utilizing vectors, and the plot windows on the right demonstrate the correlation of range between the satellites, computed receive power, and the link margin that we heard about from Nathan. The next mission plan we'll look at also utilizes the optical link object. This is an example of an interplanetary model for the Mars rover. So this mission plan models an optical link from a Mars surface rover to an orbiting relay satellite, showcasing FreeFlyer's ability to evaluate time-varying performance of surface-to-space optical communication links. Simulation configures a transmitter on the rover on the Martian surface and an orbiting receiver using a 32 ppm modulation to assess achievable bit rates and receive power throughout visibility windows, which is shown in the plot at the bottom. The scenario highlights how communication geometry, modulation parameters, and receiver sensitivity influence data throughput for planetary surface assets. Taking a step back to multi-objective optimization, this mission plan that Luke kindly helped us with utilizes the new multi-objective optimizer object to choose which asteroids a spacecraft should visit for an interplanetary mission while minimizing delta V and time of flight. The candidate asteroids are sorted by their inclination relative to the origin central body, such that the solutions are only considered for asteroids within a specified relative inclination tolerance. Optimization is performed to solve for the transfers between the origin and destination, with the objectives to conserve the desired number of asteroids to visit, minimize the total delta V, minimize the total time of flight, and also minimize the delta V for each transfer. The left-hand side, we can see the view window, and in the bottom right-hand side, we can actually see some of the recombined genomes that Luke alluded to, where we can see that the delta V is preserved for some of these combinations, but the time of flight is often reduced. And the last one we'll get a detailed look at is the multiple impulse rendezvous sample mission plan. This mission plan demonstrates how to transition from collocation to integration when solving a trajectory optimization problem. As we've seen in previous versions of FreeFlyer, collocation often allows for that fast convergence, more so than integration, but is less accurate. Switching to integration after initial collocation will improve the accuracy of the solution. In this mission plan, we actually see a chaser spacecraft, which will execute several maneuvers in order to rendezvous with a target spacecraft. The trajectory to the target is segmented into several trajectory phases, with an impulsive maneuver in between each phase. Collocation is used to attain the rough solution, and then the problem is resolved using integration. The total delta V for the planned maneuvers is calculated, and the output window here is showing us the angular difference between the maneuvers planned using collocation versus those that were planned using integration, as well as the orbital relative motion shown in the bottom of the screen here. So in conclusion, I'd like to give a special thanks to both Nathan and Luke for giving us a high-level overview of the new features developed for FreeFlyer 7.10. If you're interested in a more technical deep dive of both these new features, please take a look at Nathan and Luke's previous webinars linked in the slide deck. If you have any additional questions about the new features or sample mission plans added to FreeFlyer 7.10, please feel free to reach out to our technical support team. And with that, I'll pass it off to Danny Brown for a quick Q&A session.
All right, thank you, Nathan, Luke, and Nate. That was all very informative. We'll now take questions in the chat and ones that were also pre-submitted. So it looks like we've had a couple in the chat. Nathan, I didn't know if you want to elaborate a little more, but the first one was, how do I simulate between spacecraft and ground station pointing? Thank you, sir.
Yeah, so great question. Obviously, you can't get something for nothing with optical communications, and one thing you have to be very careful about is the pointing accuracy of your transmitter, because you have that narrow beam. So the narrow beam gives you a big win, but it also means you have to point it finer. So the good news is that this is something that I knew would be important to people considering optical comms. So we do have some built-in functionality in FreeFlyer 7.10's optical communications package to model this exact kind of signal loss that you get. So basically, you input an error for the transmitter, and then you input your beam width, and you get out a loss in, I think, dB that you'll be able to account for. It's an interesting, this is one of many things in optical communications where it's kind of a large parameter space, and this gives you the tools to explore it. Like, for instance, and you'll see this in the webinar that was just linked. There's a part where I talk through how it might seem like you want to make your beam infinitely narrow, because it's just going to get stronger and stronger signal. But if you have some finite error in your transmitter, that's going to also induce losses. So you end up with kind of a non-monotonic function that you have to optimize there between pointing error and the beam width. So anyway, great question, and it's just one of many kind of interesting components in the optical communications parameter space.
Awesome, thank you, Nathan. One of the other questions in it also is, there's some information posted in the chat, but in case you can't see it, the question is the multi-objective optimization feature available in the student version of FreeFlyer? If yes, when is this available? In a standard license for educational purposes, multi-objective optimization is not included. You would need to send a request to FF license at aisolutions.com and request multi-objective optimization, and we'll be happy to help you out for your university license. Next, we have a question for Luke. Luke, the question is, can the multi-objective optimizer be used for single objective problems?
Yes, it can be used for single objective problems, but it's important to keep in mind that because the multi-objective optimizer uses a genetic algorithm, whereas the single objective optimizer in FreeFlyer utilizes a more derivative-based algorithm. The two will be better at solving different types of problems.
Awesome, thank you, Luke. Nathan, we have another one for you. It says, are there any challenges implementing optical comms on a spacecraft?
Yeah, so this is definitely dovetails with the last question. As I said before, you can't really you don't get something for nothing, and you do have to be able to point very accurately. So that's going to be your main consideration as you consider whether or not optical communications is a good fit for you. So on one hand, the components are much smaller, and you can achieve a lot of performance with those components. So they might seem like they're very attractive for CubeSat type context, but you have to remember that as you design your CubeSat, you're really going to want some very fairly tight tolerances on your ability to set attitude in that satellite, just to make sure you're able to point that beam to where it needs to go on the ground.
Awesome. Thank you, Nathan. Well, let's just keep pressing forward with optical comms. Do optical comms work in the daytime?
Yeah, so great question. And I was definitely not an optical comms expert as I went in. So I'm pleasantly surprised to work that it still works just fine in the daytime. And in fact, there's even if for certain types of receiver, you can even have the sun in the field of view and still achieve some level of performance. And in FreeFlyer, we do model that. And we also model other bright objects passing through the field of view of the receiver. So for instance, if Venus is a very bright object, and if that happens to pass your field of view, you can model what kind of signal degradation you would get from that.
All right, thank you very much. Luke, back to you. One just popped up in the chat, and it says, what are the exposed parameters available for multi-objective optimization, including orbit params and optical comms? So maybe a two-parter.
So I'm a little, feel free to post a follow-up question, whoever wrote that, if I don't manage to answer your question, but I think maybe you are asking about like what sort of parameters are available for tuning the genetic algorithm. There are, standard genetic algorithms have things like, the rate at which variables are chosen for recombination, the rate at which variables are chosen for mutation, and the rate at which genomes are chosen for recombination. And there are a few other things like, stopping tolerances that allow you to stop the multi-objective optimizer on, as certain conditions become true and whatnot. But those are the main types of parameters that are exposed.
Hey, Luke, thank you. And he also added to that, he said, is the multi-objective optimization limited to orbits only?
Yeah, great question. So the multi-objective optimizer it's a generic kind of interface. So so the optimizer allows you to add whatever sorts of variables that you want and whatever sorts of objectives you want. So so if your problem involves orbits, you can let the variables be like the period of your orbit, the location from which you start your orbit, etc. But you can also have a multi-objective problem that doesn't have anything to do with orbits. You could solve for instance, a personnel scheduling problem using the multi-objective optimizer if you really wanted to inside of FreeFlyer.
Great. And Dave, I hope that answered your question there. One more for now, Luke. It says, when does the multi-objective optimizer know when to stop iterating?
Yeah, so I'll talk specifically about some of those stopping tolerances. One of the ways that you can stop the multi-objective optimizer is just by how many iterations it's performed or how many evaluations of the user function it's performed. Another way you can stop the multi-objective optimizer is by so there's something called the Pareto front hypervolume, and to simplify the concept, it basically just figures out how much volume or area the Pareto front is covering. So as the multi-objective optimizer evaluates more and more solutions, initially you'll see that volume of the Pareto front grow as you see, probably rapid expansion in the beginning of the solve phase. And then as more and more solutions get evaluated, it becomes harder and harder to find solutions that are better than what you already have in the Pareto front. And so the volume grows at a decreasing rate. And so you can define a tolerance for, say, if the rate at which the Pareto front is growing falls below this value, then I want you to stop. So that's another way you can stop it.
All right. And this one looks like it's back to you, Nathan. Is there a certain limit on the weather conditions, clouds, and sunlight, like with solar zenith angle threshold for optical comms link between the satellite and the laser ground terminal? Thank you for the question.
Oh yeah, that's a good one. Yeah, so the main input into weather is this visibility parameter that I talked about, and that I think basically assumes a clear sky, but with a certain visibility. So yeah, as your visibility gets higher, or sorry, gets lower, I should say, it's gonna more, I think, just because you're cutting through more and more atmosphere as you go to the horizon, it's more strongly attenuate your signal. And the same thing goes for scintillation. Basically, the lower, it's intuitive, right? The lower elevation you get, the more atmosphere that you have to cut through. So there's no specific cutoff for that, but it's more kind of like you'll be able to see that link margin shrink as you go closer and closer to the horizon. So we don't currently handle solar zenith angle, although we do pay attention to if the sun is right in your field of view or not. Or I think it's optional that you can add it. Basically, you can add different celestial bodies and their associated black body temperatures, if I recall correctly, and that'll go into the model for how much loss you can expect with that thing in the field of view. I see some other great questions. I don't know if you want to intro those, Danny.
Yeah, go ahead and take it if you can see it.
Okay, yeah, sure. So good question from Dave Schultz. Can you input C into profiles for turbulence profiling? Yeah, so great question. CN2, for those who aren't aware, is basically the way that the turbulence is kind of, I think the right way to say it is something like distributed across the air in the particular direction you're looking. So we use Huffnagle Valley, which is a very common profile. It's the Huffnagle Valley model for turbulence, and you can't input a specific profile, but if memory serves, you can set the C0 on the Huffnagle Valley, which is one of the constant parameters that's relevant to the model. And ModTran, no, we do not take ModTran profile inputs.
Right. So that's about it for the moment. Wait just a second. Oh, there we go. Got one here. Can you use real-time weather data as model inputs, such as satellite images, conditions, and radar?
Yeah. So not directly, although there is, like I said, there's a hook where you can set the visibility parameter to whatever. So you could imagine a way where FreeFlyer has various ways to integrate with external data sources. So conceivably, you could wire up a more sophisticated model into optical comms in a way where you can set the visibility via that model. And there is some flexibility there, although there's not direct integration.
All right, thank you. Any other questions? Don't see any others coming in. Right. Okay, it looks like we have tapped out on the questions. Going once, going twice, 3 times. Thank you, Nate. Next slide. All right, and now before we go, we have a few other items to cover. You can use the QR codes on your screen to book a FreeFlyer demo with any of the account executive team and our product support team by clicking the QR code. And also mark your calendars for our Q4 webinar on Wednesday, November 5th, 1 to 2 p.m. Eastern Standard Time. Our very own Justin Hartland, a flight design engineer on our Elvis contract supporting NASA and the Launch Services Program, will be optimizing long duration park orbits for Earth Escape Trajectories. There may be a computer glitch with the QR code you see on the screen, but we will get that fixed and post to your email with the slides and the recording after this, as well as LinkedIn. And for those of you interested in learning more about our FreeFlyer 8 release later in the year, you can use the QR code to sign up there. Be sure to look for the 7.10 release sometime by the end of next week. And if you need to download a license, be sure to reach out to us. On the next slide, if you have any other questions or wish to contact us, you may email us using the sales@ai-solutions.com. You can visit our website, recently updated at freeflyer.com, or simply call the number on your screen. This concludes our Q3 FreeFlyer 7.10 release webinar. We hope everyone has a great rest of your day. Thank you.